It is our great honor that Professor Greg Douglas is nominated by our committee members to have the Distinguished Science Award in High Performance Computing. And we will email you the award, after the event. And let our co-chair, Professor, to introduce Greg Douglas. Yeah.
Okay, so I send you good morning from Germany, even though I understand that you have afternoon in Asia and probably deep night in America. So it's my honor and pleasure to say some words about Craig Douglas today, who is a widely recognized colleague and a great friend. Craig is professor of the School of Energy Resources and a distinguished professor of mathematics at the University of Wyoming in US. He's also a former senior research scientist of the computer science department at Yale University. And we all know Craig also as a great organizer of many important meetings and conferences, in particular, the very successful IMEX conference in Hong Kong, which was so successful for many years. Historically, Dr. Douglas is a multiple graduate of both Yale University and the University of Chicago. He came to the University of Wyoming from the University of Kentucky and Yale University. And since 2008, he has been Distinguished Professor of Mathematics at the School of Energy Resources at the University of Wyoming, where he leads the NAMPO project. And his expertise includes extreme technical computing on parallel supercomputers and GPUs, dynamic interactions between physical models, computation, and network of sensors, with a goal to create long-running big data applications that are self-correcting and which do not need to be restarted when new data is generated. Professor Douglas is a renowned expert in multigrid methods and other numerical methods for solving partial differential equations and their implementation on modern parallel architectures. Craig has published an impressive amount of research papers which have been cited about 2,500 times, according to Google Scholar. And since coming to the University of Wyoming, Professor Douglas amassed many high-level awards, including Chi Kuang Professorship of Computer Science Award at Shanghai University in 2009. He was appointed visiting professor at King Abdullah University of Science and Technology in Saudi Arabia in 2011, 2014. He was visiting professor at Kyoto University, and he was also named the 21st Century Engineer by the International Association of Engineers in Hong Kong in 2017. So summarizing, I warmly congratulate dear Craig, Professor Douglas, to this new award of the International Association of Engineers as a distinguished scientist in the area of high-performance computing. Many congratulations, dear Craig.
Thank you. Thank you, Sergey. And thank you, Sonny, and the IAENG. And thank you to Professor Alexander Krasunki, who's not on the Zoom at the moment, but maybe will join when he wakes up. So I turned 70 years old in October. So I'm towards the tail end.
Congratulations to that. Yeah.
Yeah, I've survived that.
Congratulations.
You look much younger.
Oh, it's just because I never get a haircut since the pandemic.
Very good.
I mean, what could be better than saving money on a haircut so I can afford to put gasoline in my McLaren? Um, so um, it's a real honor to receive this, and it was really quite unexpected when I received email about this nomination. December? Um, really warmed my heart up. So I thank you from the bottom of my heart for doing this and providing this honor. Um, so I have just changed buildings to hopefully get a better Wi-Fi connection. So would you like me to give my talk now or something else?
It is a great honor to have Professor Greg Thomas to
Yes,
deliver the
please.
speech.
And the
Okay.
connection has really improved. Yeah.
Yeah, I think so. Yeah, it hasn't stopped since I changed buildings. Okay. So I'm going to actually give kind of an overview of some of the things that I've been doing with big data and dynamic applications over the last 50 years, to be honest. Um, um, in fact, I'll talk about the first dynamic application I dealt with back in the middle 1970s and how it actually operates in the modern world today, later in this talk. So I'm going to give some introductory comments in an area that Microsoft has summarized as data-intensive scientific discovery. I think of it as intelligent data assimilation, but it comes with a lot of different names over periods of time going back to the 1940s. So I'm also going to talk about dynamic data-driven application systems and big data paradigms. When you combine them, I'll call that a DBDDAS instead of a triple DAS. And I'm depending on how long you're willing to listen to me, I'll talk about some examples eventually from the energy area, environmental sciences, aerospace, and an interesting travel widget that kept me upgraded to first class during all the years I commuted between Yale and the University of Kentucky every week. And then eventually I'll get to the conclusions. There are a lot of sources of big data. Big databases is one of the most common. It's simple ones that we all interact with on a regular basis are credit card or financial databases, which are constantly growing. City and regional transportation flow is another area with large amounts of data. Environmental and disaster management comes with anywhere from a modest to a unmanageable amount of data. Oil and gas fields or pipelines or seismic imaging, particularly the amount of data that comes even from the smallest oil fields operated by a company like ExxonMobil, will completely overwhelm the internet of a big university in the United States within seconds of a data feed. Government and industry regulations and statistics is another area of data, not always big data anymore because the definition of big data keeps getting bigger and bigger. And then these dynamic data-driven applications tend to run for large periods of time and soak up large amounts of data. So the big data paradigm is become ubiquitous to society today. And historically, the data is either streamed, and if it's not used, it falls on the floor and is lost, or it's piped into databases where it can be analyzed over a longer period of time. The data frequently times out in some of these big data sets, unless you're a company like Amazon, which every click anybody's ever made to Amazon since the early 1990s is still recorded in their file systems. So the dynamic data-driven application systems was a hot area of research for the early part of this century up until a few years ago. And then it changed names first to cyber physical systems, and now it's called digital twins. It's the same thing. The people who invented data assimilation at the Goddard Space Laboratory in Maryland and NCAR for weather and climate, which invented the concept literally within a month of each other, all refer to it as data assimilation on steroids. So here, the applications and the measurement systems actually interact with each other. So the applications can ask for specific types of data, and the sensors can provide data that's not expected by the applications which have to deal with it. It's not just data assimilation adding to a given application. Because of the way the data comes in, typically it's a little more than data assimilation because you have to be able to code in order to have a defensive measure for unexpected data input. So typically, you're solving both big data and DDDAS type of problems at the same time. And these come up in many, many different areas for computer simulation. So the best way of dealing with measurements is having the ability to determine when, where, and how to get additional data that's needed to keep a simulation running longer. So a typical oil pipeline simulation program runs for years, not minutes, not seconds. It does not stop. You can replace the hardware. You can replace the software, and the system just keeps running because of the way they're built and redundancy. So when you incorporate the dynamic inputs into a standard application, you typically end up with new system modalities, and you end up with an application that's much more accurate at trying to describe what's going on in a real-world complex system. And if it all works, you end up with much more intelligent applications that can actually be programmed to adapt over time. So where's this necessary? There's a long list here on the slide. The next to last bullet is the right comment. Basically, almost everywhere you want these capabilities. And the reason is that you want answers very quickly. It says seconds to 2 weeks, but in reality, you want it now. And you're typically putting these on fairly sophisticated computer systems with a lot of computational resources. So big data in many ways became 15, 20 years ago, simply a superset of computational sciences with applications who have the overriding question: what if you had all of the data instead of some of the data? What could you do that was better? So technology limits the definition of what big data is. Okay. Every few years, the size of big data increases by a factor of roughly 1,000. And this has been going on literally since the 1950s. When my dad programmed one of the world's first oil reservoir simulators for what eventually has become ExxonMobil back around 1952, 1 kilobyte was big data for computing, because a divide took 10, 20 seconds. A multiply took 2 seconds on a state-of-the-art computer. that the company he was working for had. Now you think about what our cell phones are like, and you almost laugh. You can see why students today who are 20 years old don't understand what else old folks are talking about high performance computing. All right, so the big data dynamic applications research is really motivated by dealing with several key points that are difficult. First, you're typically dealing with out-of-sequence remote data, which may be of high quality, low quality, or no quality at all. And it's being used to try and steer simulations. So there's all sorts of problems that come up on how to clean up and deal with the data so that you get good data. There are societal gains for more accurate long-term forecasts. Typically, these come from nonlinear, time-dependent, complex scientific and engineering models. They don't have closed-form solutions mathematically. So you have to approximate them numerically. Okay, and there have been a number of DDDAS paradigms that have turned out to be useful to the big data community that's had to be transferred. And in many cases, it's been invented by a number of different groups in the data assimilation fields. So as it turns out, essentially all DDDAS applications have been dealing with big data issues as long as these things have existed. And as I implied earlier, they go back to the mid-1970s. Each project typically has invented big data concepts with no consensus on how to deal with big data inside of the field, or even how to communicate with the big data researchers until very recently. And combining the two paradigms is simply fixing a problem called reinventing the wheel, which we all know is bad science. All right, so the typical DDDAS extends conventional applications by adding a number of different things. There's a model state safe, modification and restoration. There's typically ensemble data assimilation algorithms that modify the ensemble member states by comparing the data with synthetic data of similar type that's created from the simulation state. So you have a flow where you get real data, you predict new data, eventually you get real data for what you predicted, and you can go and fix the simulation by backtracking small time units and get much more accurate future predictions. There are multi-scale algorithms that are used in interpolation. You have to retrieve, filter, and ingest data from intelligent sensors. And some of these intelligent sensors have really quite significant processing capabilities. And finally, you've got to visualize the whole mess, because the last thing you want is a terabyte of data spewed out on your computer screen in the form of floating point numbers. Okay, and the typical visualization devices might be a big LCD or LED display. It might be a tablet or smartphone, or a series of them. So the ideal sensor in this process is something that's both sensitive and selective and can communicate at high speed and with high level spatial and other relevant information, using as little bandwidth as possible. So there's a type of sensor that's referred to as an integrated sensor and processing unit, or ISP. They sense, they compute, they provide error bounds, and they're easily reprogrammed on the fly. Okay, and that becomes important if you're looking for water pollutants, for example, in a big body of water. So the big data provides you with basically a structured query language and the ability to store and retrieve data dynamically from either growing databases or data streams and get at the data easily with minimum amount of training of new people and fuss. They're flexible methods for handling large quantities of data. You could use something like a map reduce algorithm, which is simply a parallel merge sort algorithm. You need fast parallel I/O capabilities, things like NetCDD, CDF, or HDF5 or 6 or 7 or whatever it's up to, tend to be useful for dealing with large applications and distributed file systems. Typically, you use large, robust distributed file systems. And the time-dependent data retrieval tends to be based on keeping data through time windows so that you can automatically weight the data based on how recent or how long ago it was acquired. And then you have your visualization by whatever means is convenient. So there's a data warehousing process that has 6 steps, only 4 of which are used by an ISP. It can eliminate 2 of the steps. There's first the retrieval, where you get the data from wherever it's coming from. It may come directly from a sensor or database, or it might come indirectly through another computer or storage system or a large remote database that, say, a government operates. You have to extract the data. Normally, if you're getting the data in a raw form, it's a mess. And you have to find the relevant data and pull it out for use by applications. You typically have to do a conversion. The units the data comes in may not be appropriate to an application, in which case something's got to convert it to the right units. There's quality control. You need to find bad data and either get rid of it or repair it. Incomplete data, if it's going to be useful, has to be repaired and completed. Alternately, you just decide it's too bad of data and throw it out. You might store it. The data may be stored in some kind of archive, which has got to be the right medium. Is it a solid state device, a disk drive, a tape drive? Hopefully not paper tape. This might be permanent, or it might simply be temporary. If the data is not archived, it's only going to exist a very short period of time, and then it's lost if it's not immediately used. And then there's the notification process. So as new data comes in, the notification program has to know which simulations, whether they're running or need to be woken up and restarted, need the data, and inform the applications to wake up and do something with the new data. So the commonalities of this between DDDAS and big data is that all of these steps are used in both big data and DDDASs. And in both cases, the amount of data tends to be large, and there's a timeliness that has to be dealt with in order to get things to run faster than real time. If you think about it, weather prediction has not been running faster than real time for more than 20 years. For the longest period of time, it ran much slower than the weather prediction needed to be. So today, the European Weather Forecast Center is able to make 30-day predictions on weather that's reasonably accurate. In the United States, because of differences in the way the data comes and where our mountain ranges are, the weather prediction is only accurate to 7 to 10 days. So Europe is much better able to predict weather than in North America. And that has to do with the way the weather patterns across the Pacific Ocean versus the Atlantic Ocean. So an ISP simplifies the data center by getting rid of the second and third steps that we discussed. The data is delivered from the ISP as high-level information tokens, and typically is very succinct in size, does not require a lot of extra communication bandwidth, and the bad data has been dealt with so that potentially a third step in the data center process can be eliminated as well. All right, so let me turn to some real examples. I'm going to look at oil and gas pipeline networks because that's what got me started in this field. That's why I own a McLaren, because this was done as a private company that my father co-founded, and I worked for, actually. Then I'm going to talk about one or two applications in environmental sciences. I'll probably talk about the water contaminant backtracking. I might talk about the wildland fire modeling. The aerospace one is kind of intriguing because I've flown 6 million miles on United and Delta jets, and I find technology major advances in that area to be interesting. They're basically a dynamic data-driven application system. And then travel. I'll talk about a unique travel DDD-AS that ran for a number of years. So for oil and gas pipelines, you have everything from production platforms offshore with a submarine pipeline. You have onshore wells, you have pipes, you have tank farms, you have pumping stations, you have above or below ground pipes, you have booster stations that may be necessary to pump oil or gas over large distances. But amazingly, this picture is in a dictionary. So let's look at a real pipeline, the Alaska pipeline. This is a 4-foot in diameter pipeline, runs from the north of Alaska to the south of Alaska. The picture on the bottom is me standing by the pipeline near Fairbanks, Alaska, on my one trip to Alaska. The picture on the top is a piece of the pipeline with what's called a pig. This is a separator or cleaning device that you put between medium. So typical pipelines for these range anywhere from 5 centimeters to 5 feet in diameter, so not less than 2 meters. They're rarely straight. They're rarely level. They contain, typically at the same time, different grades of oil or gas. They have separators. They have sensors, both inside and outside. And this type of modeling is not restricted to oil and gas pipelines. It works for general chemical and also things like water pipelines for a city system. Now, what you can't see is attached to this piece of the pipeline was a sign. On the sign, it said, if you see any emission from this pipeline, turn and run 1 kilometer away from the pipeline as fast as you can before it explodes. Nothing like a friendly reminder that you're not really at a tourist site. So in the 1970s, when I got started with this, the problem was modeled mathematically based on time-dependent, nonlinear coupled partial differential equations. There were 2 different models, and depending on the situation, you could switch between the two models to see, to get a more accurate prediction based on the input. There were sensors in all the pipeline components. The computing was not centralized. It was distributed. So scattered all around the pipelines were old-fashioned telephone booths, complete with a door. On top of the telephone booth was a heat pump. Worked well in Saudi Arabia or Canada, where you needed either cooling or heating. And inside, you had two mini computers, 4 array processors, and a US coin, a 5-cent nickel, soldered into the telephone, which allowed free telephone calls to be made outgoing from the computer system. Calls could also come in and be answered by the computer systems inside. The sensors provided not a lot of data: temperature, pressure, and velocity. And the data arrived dynamically based on the needs of the simulation and any anomalies that were being noticed by the controlling system. There was a central control site, but the computing was completely distributed. So in 1978, for the complete Saudi Arabia oil and gas pipeline network, they received 2,000 pieces of telemetry per minute on average. So let's move forward. Today, they use 3D math models instead of 1D models. They have topography. They don't do grid computing anymore. They use centralized computing. They use fiber optic or TCP/IP transmissions. They typically have a gigabit Ethernet as a backup to the fiber optics that's attached to the pipelines. There are many, many more sensors that are used. They now measure the pipe shape changes, internal pollutants. They can pick up external gas leakages. So after 20 years, the Saudi Arabia system was replaced. Now, it never shut down for a minute for 20 years. During that time, they replaced hardware and software, but could keep the system up because of compatible upgrades. So in 1998, they were getting approximately 100,000 times as much telemetry per minute. I was able to talk to the people running that system while I was at KAUST roughly 10 years ago. And at that point, they no longer could count how much data they were receiving per minute. They had no idea how much they were getting. All they knew was it was described as a tsunami of data. In 2025, they get much, much more data than 10 years ago. So in the 1970s, there was a primitive center where they ran what-if scenarios just to keep the pipelines from breaking in parallel with regular monitoring. Today, if you see one of these centers, it has very large-scale visualization that monitors the pipelines. There's a multi-scale framework. The Saudi Arabia or Saudi Aramco Control Center has a 35-meter long set of displays that shows what's going on in their pipeline systems. They're still merely trying to find anomalies in the data streams to avoid pipeline systems. And a good example is when you change media, there is a pressure change that goes the whole length of the pipeline. And if it gets out of control, the pipeline will rise up. It's underground by, say, 6 meters. It can rise up 6 meters above the ground. That's a 12-meter rise. And if the pipeline is not built right, it will break, causing a horrendous mess. Okay, and Aramco actually tested whether the system in 1978 was accurate and found that it was accurate to within about 50 feet. So that's 15 meters of the actual places where they had incidents. All right, so let's go look at another example. Let's look at water contaminant backtracking. So the goal here is that you're monitoring a body of water, which could be a lake, a lagoon, river, all sorts of things. Could be an aquifer underground. And you'll start seeing clouds of pollution from the sensors. That does not mean they're telling you exactly where the pollution is. In order to alleviate the problem, you actually need to backtrack in the model to identify who the polluters are and stop them. Okay, so in this case, we have sensors, we have hydrodynamic and contaminant transport models, we have the data assimilation system, and you have to have a variety of components in hardware and software in order to provide a unified disaster management and mitigation system. So here's where an ISP is really useful. So in our case, we built what we called a solid state spectral imager, or SSSI. It was designed to collect hydrological, geological data and perform chemical analysis. What we built was small and light enough to be mounted on roving platforms, carried in the palm of your hand to do remote sensing. And it typically had a scan range between 10 and 100 meters in distance. So it was small, but it can actually measure a fair distance. So we were using either an LED, which was cheap, or a laser diode array, which was much more expensive. And one of those got sent to Mars by the guy who created this stuff, Rob Lauder at the University of Kentucky. They have photodetectors and onboard processing. They can combine innovative spectroscopic sensing with a hyperspace data analysis algorithm, and you can combine it with a radiation detector. So in the upper left is the little handheld LED device, as well in the center, so you can see how small it is. The bottom was one of our rovers. There it's set up for moving on land. But the lower right picture is you could put a paddle on the back, seal it up to make it waterproof, and put it in water. And we used it in water bodies for looking for certain types of water pollution. So this thing used near infrared, visible, and ultraviolet light. We also put a radiation detector on it at one point. Almost any organic compound has a near infrared, possibly combined with radiation signature, that can be measured by this little device. And it was field reprogrammable. So particularly in bodies of water, if we found some kind of interesting chemical trace, we could upload a different part of the library to sense for other chemicals that might point us towards certain types of pollution. It turned out it was also useful for potential undersea or offshore oil and gas work as well, for putting in new wells. So you could use this to invoke the appropriate application when things were found. And you could change the sequence of the light pulses on the SSSI to look for very specific other chemical traces. Okay. Okay, so the contaminant model was a multi-scale ocean model plus an advection diffusion equation. This simulated the trajectory of contaminants as they were carried along in the simulated flow. We found it worked pretty well in estuaries, lakes, and aquifers. The data assimilation reduced the computational errors by a very large amount, and it improved our predictions. First, we used the set of measurements, and then as new data came in, we were able to refine the predictions. So one place we collected data, thanks to an environmental government agency in the state of Rio de Janeiro, was in the lagoon in Rio de Janeiro. Inside that lagoon, there's a series of sensors offshore. The water leaves by 2 channels and only comes in one channel. It's highly restrictive, what's in there. So one of the cases that we caught, and we saw this multiple times, was the data which show a large smear of pollution. And we could backtrack using our simulation models to try and find out, was it one source of pollution or multiple? So in a number of cases, after 10 time steps, we saw it was looking like about 2, and then it became more refined after another 10 steps. And after about 40 time steps, we could refine it down to the actual number, which in this case was 2. So once they knew where the pollution was at that time, they could go look on the shore over here, back here, over here somewhere, and typically find the polluter and stop it, and very quickly. The lagoon in Rio de Janeiro has extremely pure water, which is highly unusual around Rio de Janeiro, which is highly polluted. So we ended up developing a least squares Bayesian approach. It gave a high acceptance rate, which accounted for the uncertainties associated with the sensor data. And in particular, we could prove that the rigorous sampling that we needed could be done using this mathematical technique. Okay, and the approach is very similar to Kalman filtering. And it turned out the inverse problem could trivially be solved using large data streams, unlike a lot of inverse problems, which are computationally expensive. We had enough data to actually solve these things with almost no computational effort. So the big data advantage here was that we streamed the data using sliding windows, and the inverse problem was solved using the sensor data with the associated least squares problem. So the amount of data generated was quite large, but we were able to filter it down typically so that we could make movies by saving the data every 10 or 100 time steps. The visualization allowed finding patterns that were useful much more quickly. All right, I'm going to skip the wildland fire modeling for time's sake. It did have some interesting issues dealing with satellites and how composite JPEGs are rarely completely sent from a satellite, but that's another issue. Well, let me go on to the smart airfoils, starting with the Boeing 787, copied by the Airbus 350 a couple years later. You have the airfoils change shape in flight. Okay, the first commercial flight with something like that on it was in 2011 when ANA, All Nippon Airways, flew their first 787 on a commercial flight. The wings change shape based on an automatic sensor simulation using a predictor-corrector artificial intelligence system that's sitting on a computer inside the airplane. And it's trying to predict the airflow during turbulence. The wings can change their configuration and shape in 2 seconds. So what it's trying to do is get as best a airfoil or wing configuration as possible for the oncoming turbulence. So this is very important for 4 months a year to the east of Tokyo on flights heading across the Pacific. There is a area that starts about 200 kilometers east of Tokyo and has a problem for up to an hour of flight time, where an airplane gets into a turbulence where it starts acting like a rocking chair. And by changing the configuration of the wings in the right patterns, you stop that. Okay. I used to like it because I'd go to sleep and I'd wake up and we were across the Pacific. Now it doesn't put me out, so I have to deal with the flight across the Pacific. And unfortunately, I come to Japan 5 times a year. So if you're by a window, you can actually see the wing change shape, which in the early days of the 787 actually caused panic on the airplanes. The actual total number of shapes of the shape memory alloy metal lines that are in the wings to change the shape is a trade secret. There have been guesses as to how many there are for both Boeing and Airbus, but nobody's ever admitted to it. So Boeing said all their future airplanes will have this, and Airbus hasn't ever made an announcement, but appears to be doing the same thing. So for a long time, engine intakes and exhaust had these shape memory alloys, going back in fighter planes to the 1960s and 70s. The main reason for using them on commercial airplanes is to make it very difficult to fire a heat-seeking missile when they're taking off or nearly landing to hit the airplane. So it's a security issue. So let me talk about the last one of these things, the flight cast. So this was a dynamic data-driven application system designed for frequent flyers, particularly people who commute by airplane, which I did for 10 years. So you model airplane connections for given routes and days. And the project gets broken down into multiple functional units. There's sensors that poll and collect data from a variety of sources, including airlines. There's a transport of the data to get it inside the DDDAS, and you need a significant data store because you really need at least 1, if not 2 years worth of data to make this significantly accurate. By significantly, say 98% correct. There's a predictor which predicts delays and a corrector that analyzes the accuracy of the predictions and modifies parameters for long-term use. Okay, and it uses the big data to solve the inverse problem that's involved very cheaply, just like in the water contamination case. So this is kind of what it looks like. You have current data that's coming from a variety of places that I'll talk about. It's fed into both the predictor and the corrector. The corrector sends weights back to the predictor. You're getting flight and weather data. You can adjust how often you poll for the data. You save historic data, and eventually you get a prediction, which you have to live with. So in fact, what my students programmed was a Delta Airlines sensor, a United Airlines sensors. They were collecting data from 2 sources, but they sometimes collected from 5. They had the Dr. Douglas sensor. They had spyware on my cell phone, or what you would call spyware. So they could tell where was I based on the GPS in the cell phone. There was the so-called data center receiving, where we got flight data, weather data, actual after-the-fact weather data and actual after-the-fact flight data. So there was collected stuff. There was a variety of parallel data center processing that was going on. We had multiple predictor models. We had both an A model and a B model, and we had n cases of each running. And then, based on all of these predictions and the corrections that were going on, we got predictions on when flights would get canceled or delayed so much that I couldn't make my connection because I always had 2 flights home or 2 flights to the other office, shall we say. So the major components were the sensors, and these were software agents, not hardware. On our side, we were collecting data from other people's computer systems. We transferred the data between our software agents and the other parts of the DDAS. The data store was a central repository, which at the time we were doing this ended up being quite a few disk drives. Today, it would, of course, be 1. The predictor tried to predict flight delays and cancellations based on both the current conditions, the expected conditions for the flight time, and historical data. And the corrector analyzed the accuracy of this and improved the accuracy over time by changing the weights. Okay, so the travelers, well, they needed something to track the traveler location before, during, and after flights. There were monitors. You had to monitor preferences. Do you want on time? Do you want misses? Do you want to maximize frequent flyer miles given conditions? You have to make a change. The airlines were making very low-level web requests to avoid graphics, ads, cookies, and everything else, which monthly had to change because the airlines didn't like people doing this. We used tools that were effectively constructing very simple compilers for the data. The weather, we needed wind speed, direction, visibility, temperature, type of precipitation. We could have asked for more, but that seemed to be a lot. We got a lot of data from the airlines and the weather sources. The Transportation Security Agency, the TSA, provided us with nothing useful. Absolutely nothing. Worthless websites. So the seasonal and location-specific trends required a year training period. In the case of weather, we could build up several years worth of data just based on the airports and the weather historical data airports to build a database that was very helpful towards jump-starting the system in the first year. The transport was code that was Java-based. Greek computing was enabled, and we used a standard SQL database. The predictor corrector. The predictor combined the data from all of the sensors, weighted the data, produced a probability from 0 to 1 of a significant delay or cancellation, and each factor in the probability was produced using fuzzy logic, not pure numbers. The corrector reviewed the results of the predictor on a regular basis. It was a fairly inexpensive computation, and the main purpose was just to adjust the weights. So the predictor correctors ran on multiple times before the actual flights, and the corrector then once after the actual flights. So building up the database of flight information generated a lot of data, even from 2 airlines. What we wanted from this, or what I wanted for this, was a prediction 4 days in advance of my flights on whether these flights were actually going to work. Why 4 days? Upgrades to first class in the level of loyalty or frequent flyer programs could only be made 3 days in advance for domestic flights in the United States. if I had to change my flights, I wanted an upgrade. Okay. I didn't want to sit back in roach class. No offense meant to everybody who's ever sat in roach class, including me, for millions of miles. But first class is better than roach class. Okay. Neither of the two airlines tracked anything like what this flight cast did. And sadly, there's no tool similar to this that's ever been commercially made available. When we talked to the travel industry about commercializing this, the first thing the airlines did was to go to court to tell us we couldn't do it, not with their data. So that killed it for a commercial tool. This ran for several years. It was very helpful. I managed to stay out of roach class every flight for, I think, 3 or 4 years running, which says a lot because a certain percentage of the flights got canceled. The other thing is, after about a year, this thing was 95% correct. After 2 years, it was more than 98% correct on predicting airline failures. And that was very helpful to me. All right, so let me conclude the talk, since it's almost been an hour, that these dynamic big data driven application systems have a lot of common components. First, you've got sensors that provide the data with potentially known error bounds within time constraints. You need to use correct sensors, and they need to be chosen to provide good data from specified locations. You know the data is not necessarily accurate, complete, or timely, but it's going to arrive anyway, and you need to have some kind of sensible processing of the data, which could include throwing it away. And the sensors preferably should be dynamically reprogrammable. There is a rapid error growth in new data when steering is unavailable. And this frequently means that simulations have to be restarted. So in the oil industry, for long periods of time, they set up initial data and ran a simulation, got a prediction over a period of time. And while that was running, a little while later, they'd start up yet another identical simulation with a new set of initial conditions and get a movie out of it, and they would try and combine them. Today, they don't have to do that. They can just run one simulation and keep it running. The application models, numerical methods, and significant items that are tracked may have to be changed due to the incoming sensor data, and it may require a human in the loop to steer it. It might not be fully automatic. You get very large amounts of input and output data. It's difficult to analyze. Frequently, the visualization of the output data is not optimal. It's not exactly what you want, and you have to figure out how to fix that. And the last key components are that you end up with much longer running simulations, providing you with short-running simulations. You typically combine the results into video or predictions. And as a result of being able to have one simulation that's providing better results, it's easier to analyze. The visualization can be managed better. The whole computation can be accessed. And frequently, if you're using the big data paradigm and some kind of ad hoc data management methods, you do much better than the people who are just winging it with the data they're getting on typical application simulators. So this has been a very nice area of research. It dates back to World War II in Britain, when they used people and telephones to provide data about where the German aircraft were that were coming to bomb England. They had radar, which the Germans did not know about, nor the Americans for that matter. And they were combining the people with the radar systems to get a much more accurate prediction of where the Germans were going to be bombed. And then in the late 1969, to be exact, was the key year where the data assimilation concept was really developed and put to use in both climate and weather prediction and in space predictions for spacecraft, satellites, and whatever. With that, I'll stop. Thank you.
Yeah, thank you. An interesting speech on the big data. As we note, the data size increased very rapidly. Fortunately, the computational power also advanced with the new hardware and also the network connecting, because the internet had also technology had advanced that large amount of data can be transported, by the internet.
Yeah.
It is an interesting topic.
Yeah.
And so next friend, Professor Greg Donners for the our distinguished science speech. Thank you.
Thank you very much. I look forward to seeing the proof
and
and
so
having it posted.
And warmest congratulations again, Craig.
Yeah, thank you very much. Very great honor, and I really appreciate it.
oh, it's our honor.